Your first, the packet part of this, right? So the packet part, we're gonna skip through page 1 today, we'll come back to that. We're gonna move on to the factoring refresher on page 2. So it should, you'll see this, this text, right, top of page 2. All right, so for today, this is nothing but 100% just practice, kind of reminder, quick review of how we factor stuff. So I'd like phones put completely away, please, earbuds, all that stuff. We gotta get through, we're gonna do a lot of review today.
Hell yeah, bud.
Okay, so first of all, we want to ask the question, what is factoring, right? Because we throw that word around a lot, and you might have an association with factoring that you did back in, why don't you get rid of that? Back in Algebra 1. Oh, there's just hanging there, I got you. And you might remember what that process is, but factoring is nothing that mysterious, right? Factoring is stuff in a way, you've done it way before Algebra 1. Earlier in life in your pre-algebra classes, you did it as well. All factoring is the opposite of multiplying, right? So like we would say 2 times 3 is 6 is really simple. And normally it's much easier to multiply than it is to factor. Not much, but it's easier to multiply than factor. So that process of starting with 2 times 3 and getting the answer 6, we call multiplying, right? But if we reverse that process, what if we start with the 6 and we end up with 2 times 3? Okay, what have we done? Well, we've broken the 6 up into a product of factors, right? 2 and 3 are factors because they're things that are being multiplied, right? That's all factors are things that are multiplied, okay? So we're breaking 6 up into a product of its factors. And so that's what we call factoring, okay? So the goal for today, obviously, is not just to deal with numbers, it's to deal with algebraic stuff. So we have some variables in there. So let's look at another example, simple example. What if I want to multiply out? Let's start by multiplying, and then we'll talk about how we could reverse that process and factor. So what if I want to multiply x plus 3 times x minus 5? And we'll do a lot more of this stuff later with bigger expressions when we get to polynomials. But you've done this a million times. Isn't that just distributing? If you multiply, you might have called it foiling or distributing or something like that. They mean the same thing. If I'm multiplying one factor times another, and these factors are not just numbers, they have variables in them, right? There's more than one term in each factor, more than one thing that's being added or subtracted, right? Then don't we just distribute, like we'll take the first factor and the first term is an x, so we'll just distribute that x to both parts, and what do I get? If I distribute the x, what's x times x? X squared. X times negative 5. Good, right? So there's the first 2 terms of our answer, 2 parts of our answer. And then we distributed the x, so now we have to distribute the 3. 3 times x is, and 3 times negative 5 is, good. And then if we just added all those terms up, what are we going to get?
X squared minus 2x.
Good, because the negative 5x and the 3x are like terms, right? Okay, so here's what we got. Same as before, the process of starting with the separate factors, x plus 3 times x minus 5. What did we just do? Well, we just multiplied, didn't we? So once again, we could call that multiplying. There's kind of a fancier word when we multiply out stuff in math where we have variables, not just numbers. Then we call that expanding. But it means the same thing. Okay. Crystal, why don't you put that away? So why do we call it expanding? I guess because we're turning it into a bigger expression when we multiply stuff out, right? Okay? So that's easy. You guys are good at that stuff. You've done that a whole bunch. But the thing we want to review is the opposite. What if I'm going to start with x squared minus 2x minus 15, and I want to break that into a product of smaller factors? Okay? I want to do this. That's factoring. And I'm not going to talk today a lot about why we do that. but it's an important way for us to solve equations, right? Factoring, we're eventually, in Unit 4, we're gonna come up with a whole slew of options, like 4 different options for solving quadratic equations. And we wanna pick the one that's gonna be the easiest to use, right? So sometimes that's factoring, sometimes it's not. But when it's the easiest one to use, we wanna use it, right? Because it makes our lives simpler. And it's, we'll get into that later, but for now, we're really not gonna focus on why we're doing it. We'll look at that a little bit more tomorrow. But for today, we're just practicing this process. Okay, so the first part is greatest common factor, factoring out a greatest common factor. Okay, and let's look at a quick example. Like, what if we wanted to look at the greatest common factor of just numbers? Like, what if we picked 12 and 18? Okay, so let's do like a problem 0 here, where we don't have any variables in there at all. So let's find the greatest common factor of 12 and 18. What is it? 6. How come? Say it again. Okay, but that's actually not why. What do you think, Tyler?
It's just the biggest number that goes into both of them.
Good, it's the biggest number that divides into both of them, right? That's what we're looking for. The greatest common factor is the greatest number. If we're just talking about numbers, it's the greatest number that divides evenly into 2 or more expressions, right? 2 or more numbers. In this case, it's a 6. Okay, so we can see that pretty easily because 12 and 18 aren't huge numbers. What if they were? What if they were? There's another way we could go about this, right? We could, if those were really big numbers and we wanted to find the biggest possible number that divides into them, we could use a factoring tree for both of those. And that would be an easy way to do it. We don't need to here, but what if we did? What if, once again, what if they were really big numbers? Let's look at how that might work. What about the number 12? If I make a factoring tree out of that, remember, all the factoring tree is, which is gonna, as we move downward, it's gonna always branch. It's gonna branch into products that multiply to the number above. So what are some numbers that multiply to 12? 2 and 6. I mean, we could do 2 and 6, or we could do 3 and 4. Doesn't matter. We just need 2 numbers that multiply to 12. So if we do 2 and 6, can I split 2 up? No, 2's done because now the only number that divides into it is 1. So that's a prime factor, right? What about 6? 2 and 3. Okay, so now let's do 18. What are numbers that multiply to 18? Say it again. 6 and 3. Okay, so 3 and 6. 3's done, right? What about 6? 2 and 3. And now we just want to look for, are there common prime factors? Let's find all the ones that are common. Yeah, there's a 2 and there's a 2, right? So they have a common prime factor of 2. This one has another 2, but this one doesn't. It only had 1. And then we also have a 3, right? So then each of these has the common prime factors 2 and 3, and so the greatest common factor would be 2 times 3 is 6. That's another way we could do this, if we needed to, right? So the greatest common factor for this guy is 6, all right? Now, what if we introduce variables? Okay, so what if we're looking at the greatest common factor of 12k and negative 18? Well, 12 and 18, that still is 6, right? What about the k? Does k, let me ask you this, does k divide into 12k? Like 12k divided by k, that works, doesn't it? Don't the k's just cancel? But what about 18 divided by k? There's nothing to cancel, right? So I can't include a variable in my greatest common factor this time. The greatest common factor for this one is just 6, right? I couldn't get a number to come out of it, or a variable to come out of that. What about example 2? What about example 2? What's our greatest common factor going to be here?
8, 9, 7.
So let's look at the number part first. What's the biggest number that divides into 40 and 64? It'd be 8, wouldn't it? be 8. Good.
Okay.
So we get 8, right? Now let's look at each of the variables. We've got x's in there. Okay, so what about the x's? So, Lakaya, what do you think? What's going to be the biggest power of x that I could divide into each of those? I've got an x to the 8th in the first one and an x to the 4th in the second one.
4.
Be 4, exactly. It'd be an x to the 4th. How do we know that? Well, think about it this way. What is x to the 8th divided by x to the 4th? Let's remind ourselves how that works. X to the 8th divided by x to the 4th is what? X to the 4th, because when we divide like bases, what do we do to the exponents? We subtract. Good. So we get x to the 8 minus 4, which is x to the 4th. So it does divide evenly into x to the 8th. And it also divides evenly into x to the 4th. But I couldn't divide x to the 4th by x to the 8th, could I? It wouldn't work, right? If I tried to do that, x to the 4th divided by x to the 8th, I'm going to get x to the 4 minus 8, which is x to the negative 4. We don't want to have negative exponents there. What does that look like if I were to write out x to the 4th? That's just x times x times x, isn't it? Now what that means when we have x to the 4th? And x to the 8th is just x times x times x times x, etc. Look what happens here. I could cancel out 4 of those, but then I've still got a bunch left on the bottom that are uncanceled, so it doesn't work. You get the idea. It's probably overkill, right? So we get x to the 4th is the biggest power of x I can divide away. And then finally, what about the y's? I can just divide by y, okay? All right, so then that's my greatest common factor. That's what's being asked for in this question. But later on, like on Moodle, I'm going to have some questions where I want you to write that as a product of factors. Write it in factor form. Okay, so then what's that going to look like? I'm going to end up with my greatest common factor. Here, I'm going to do this a little differently. Let's go. Okay, so this is going to equal, my greatest common factor is 8x to the 4th y, but what's going to be left behind when I divide that away? Well, let's find out. I could just divide each of these terms by 8x to the 4th y and find out. 40 divided by 8 is what? 5. Okay, so I know the number part is going to be a 5. X to the 8th divided by x to the 4th is, you already told me that's x to the 4th, and the y's canceled, right? So that's my first term that's left over. When I divide out the common factor, x to the 4th times y, 8x to the 4th times y, what's left behind from the first term is a 5x to the 4th. Okay? Well, this plus sign, I'm going to put a yellow circle around it so we know that those are the same plus signs, right? Now, what's left from the other one? So now I've got, if I divide this guy by 8x to the 4th y, 64 over 8 is what? 8. And then look what happens here. The x to the 4ths cancel and the y's cancel, so all I'm left with is an 8. Okay? So if I wanted to, if the question just said factor this, that would have been my answer. Here's my greatest common factor, and here's what would be left behind, right? How do I know it's right? How could I check? Just multiply it out. I could just distribute the 8x to the 4th y, right? So in a way, when we're factoring out a greatest common factor, what is that? I'm just undistributed. That's really all that is, right? Factoring out a greatest common factor is merely undistributing. I'm going to write that down up here. It's so important, I'm going to write it down. Okay? Get the idea. Let's try another one. How about this one? What's my greatest common factor? So what's the biggest number that divides into all those? I think I heard it.
Oh, 7.
7. There you go. Okay, and then I've got m's. What's the biggest power of m I can undistribute? There you go, an m squared. And then what would be left behind if I wanted to write this as a product of factors? I've got my greatest common factor, which is 7m squared, and what would be left behind? Okay, so if I divide the first one by 7m squared, the first term, 14 over 7 is 2. M to the 6th divided by m squared is m to the 4th. So there's the first leftover. How about the next one? Negative 35 divided by 7 is negative 5. And then m cubed divided by m squared is m. Good. And then finally, negative 7 divided by 7 is negative 1. And look, m squared divided by m squared, those would cancel. So I just get a negative 1 there, don't I? Okay, so we could say then, really, that this if we wanted to label these parts, well, we know this is the GCF, the greatest common factor. This part over here, we could kind of just call the leftover if we want to. Right, that's what's left behind when we undistribute the 7m squared. Okay, one more of these. This one seems pretty easy, but everyone in here is about to have a question for me on this one. Where's your phone at? It's just stuck up. Well, I don't want it there, because if it's there, you're just going to look at it again. Okay. Are we going to have to do this, seriously? I mean, when I ask you guys to put that thing away at the start of class, I want it put away, right? Okay. Why do I want it put away? Do you think I really care if you're on your phone? I mean, does it impact my daily life if you're on your phone? No. Outside of school, I couldn't care less. But what does it impact? Your learning. That concerns me, right? That's why I do what I do, because I want you to be successful, right? So you got to meet me halfway on that, right? I mean, it's time to be adult enough to know that you don't eat chocolate cake for breakfast, right? You guys wouldn't do that every day, right? Well, you can put your phones away during class too, I think. All right. I don't want to have to ask you that again, Trent. Agreed? Agreed. Okay. So, what's the question everybody's got for me here?
What the negative and the positive?
Yeah, exactly, what do you do here? Because I've got a negative term and a positive term. And so there's the question, and I get it, that's a question, it could go either way, couldn't it? Well, here's the rule. We go back to this page right here, here's the rule. The greatest common factor inherits, the sign of the leading term. That's the term with the biggest power of x. As we're going to find next unit, that's the term that just dominates the behavior of that polynomial. Okay. So in this case then, well, x to the 4th is bigger than x squared, isn't it? So we know that the sign of the greatest common factor would be negative. Okay. So what are we going to get here then? We know it's negative. What's the biggest number that divides into 20 and 36? And what power of x? There you go, right? And so if I wrote this in factored form, I'm going to get my greatest common factor is negative 4x squared. What's going to be left behind? So negative 20 divided by negative 4 is good. And then the x squared. X to the 4th divided by x squared is x squared. 36 divided by negative 4 is negative 9, right? And then x squared divided by x squared cancels. Okay, good? All right, so next step. We're going to skip that for now. We already did one of those. Okay, factoring simple quadratics. And this is probably, I don't think we're going to get, this might be as far as we get today. That's all right. Simple quadratics. What makes them simple? Well, these are in, would everybody agree here that these are in, all three of these examples are in the form ax squared plus bx plus c, right? And maybe it's not an x, maybe it's a w or an n, but it doesn't matter what the variable is. The pattern's the same. Ax squared plus bx plus c. And in each of those cases, what's the coefficient of the squared variable? What's being multiplied by x squared or w squared or n squared? 1, right? That's what makes these simple. What makes these simple quadratic trinomials, trinomials meaning they have, tri means 3, right? They have 3 terms, is the fact that a is equal to 1, okay? So if I want to factor these, I'm just trying to write them, trying to break them apart into a product of simple factors, okay? Well, we know what's going to happen with the x's. We already looked at an example back here. How did I get an x squared there when I multiplied these out? Because x distributed to x is x squared. So then we already know that if this is going to factor, and it could be that it doesn't. In some cases, things just don't factor easily, and we give up and go on to plan B, right? But in this case, what would have to go there and there for us to get an x squared? It would have to be an x, right? That part's simple. The part that's a little bit tougher that we have to focus our attention on is what are the numbers that go with it, right? The magic numbers. So these are the rules you may have forgotten. But the magic numbers, what do they have to do? When a is equal to 1, there are always going to be magic numbers that multiply to the constant, right? So they're going to multiply to c. So in this case, that would be 45. And they're going to add to b, the coefficient of x. So in this case, it would be 14. Okay? And so here's how I would encourage you to approach this. You always want to, first of all, ask yourself, well, what are the signs of the numbers going to be? Let's play the sign game. If they multiply to a positive, what does that tell you? They're either both positive or both negative. But in this case, because they add to a positive, which one is it? They're both positive. And now what are the numbers that multiply to 45 and add to 14? 9 and 5, there you go. 9 and 5, good. Okay, so it's factored. How could I check it? Multiply it out. Distribute and add up like terms, and I should get this back if I multiply it out, right? Okay, what about number 6? Okay, what do they have, my magic numbers this time, they have to multiply, that's, I won't do that. Multiply to 26, and they have to add to what? Okay, so what are the signs going to be this time? I know I'm getting W's there and there, right? And now I know they're both going to be negative, because if they multiply to a positive, they have to be the same. And if they add to a negative, they'd both be negative, right? So what numbers fit the bill? What numbers multiply to 26 and add to 15? 2 and 13. Okay, good. And it's factored. Okay, what about number 10, last one? So I know I've got n's. If they're multiplying to a positive and adding to a negative, I know that they are both negative, right? And then what numbers multiply to 1 and add to 2? What is it again? 1 and 1. So that's factored correctly, but that's not written in the simplest form. How would I write something times itself? Squared. Okay, so the best way to write that would be n minus 1 squared. Okay? All right, so now, moving on, what about one like this? This is one step harder, right? Because what's different now? Well, now a is not equal to 1, a is equal to 2. And that makes things a little tougher. Right, we're going to practice that. This is as far as we'll get, probably. Okay, but does this one have to be so hard? Do we have to, you remember doing bottoms up probably, right? Bottoms up is what you do when you're trying to factor a trinomial where a is not equal to 1. It's a little bit harder process than what we do if a is equal to 1. That's pretty straightforward and simple. So are we going to have to go into bottoms up on this one? Or did you learn that way, or did you learn slip and slide?
No, either of those.
Did you do slip and slide? Okay, well, we're going to review it today, so it'll be. Okay, but here's the good news. Here's the good news. We don't have to do it here. How come? What can I do before I do anything? What can I do? Is there something that divides evenly into all those?
Yeah.
2 does, exactly. And this is our general rule. We always want to look for a greatest common factor. It's always going to make our lives easier if there is one, if we're factoring something. So the very first thing we could do here is we could undistribute a 2, right? So right away, we can write this as 2 times what's left behind when I do that. 2k squared divided by 2 is k squared. Negative 16k divided by 2 is good, and negative 40 divided by 2 is okay. Look at that. See, look, that's good. Now we've got 2, our greatest common factor, times a simple quadratic trinomial where a is equal to 1, right? So I know then that I'm going to get my 2 out front. There's my greatest common factor. But this trinomial, hopefully, is going to break up into 2 small factors. If it does, what has to go there and there? I'm just working on this part now. Those have to be k's, don't they? And what would my magic numbers have to do here? They have to multiply to what? Okay, so they're going to multiply to negative 20, and they're going to add to what? Add to negative 8. Okay, now this time, if they're multiplying to a negative, what's that tell you about the signs of the magic numbers? One's positive and one's negative, right? If they're adding to a negative, which one must have been bigger? The negative, right? Because when they canceled out, if it ended up being negative, so the negative one must have been bigger. So let's put that one first. We get a negative and a positive, and now let's just figure it out. What numbers multiply to negative 20 and add to negative 8? Ah, there we go. Negative 10 and positive 2 works, doesn't it? Right? And so now we're done. It's factored. Okay, but the moral of the story is we didn't really have to do anything fancy there if we just factored the 2 out first. Are we out of here like in 1 minute? Okay, so we might have room for one of these. So what about one like this? What about one like this, where a is greater than 1? And this time there is no greatest common factor, right? Okay, so this is where we go through the process of, in fact, let's skip ahead. We go through the process of slip and slide, okay? You remember, hopefully you guys, this is what you called it?
Sure.
And probably Mr. Morioka called it that, is that right?
Some of us.
Or Mr. Hagwood, okay, Mr. Hagwood, yeah. So I've never used this terminology before, but we're going to give it a try. So here you are, go with the last thing we want to get through. So focus for another couple minutes. So what do? We've got, this time we're factoring polynomials of the form ax squared plus bx plus c. The a is there because it's not 1 anymore, right? So the first thing we do is we're going to slip a to the end of the trinomial, and we're going to multiply by c. Okay? So let's try this with an example. Like, what if we take this one? And we'll just go through the example while we do this. Okay, so let's do step 1. So step 1. Step 1, what do we get? What's a times c? 2 times 18 is what? Okay. Okay, step 2. Step 2. We're going to factor this new basic trinomial. So what we mean by that is then for step 2 is we're gonna take the trinomial x squared, we're gonna take the 2 and we've slipped it to the back. So we get x squared minus 15x plus 36. Okay? So let's factor that. What are gonna be my magic numbers that multiply, get x's there? What numbers multiply to 36 and add to negative 15?
18,
No, they gotta both be negative, right? Because they're multiplying to a positive and adding to a negative. I heard it, 12 and 3. Okay, is that right? Everybody with me? Yeah, how come?
I don't know.
Okay, well, get with me. That's on you. Okay, step 3. Step 3. Divide both of your factors by the value you slipped over in step 1. So what A was? So we're going to divide both of those by 2, right? Because there's A. That's the value that we slipped. So we're going to divide each of those by 2. Okay, so that's my step 3. And then step 4. Step 4, all it is we're going to reduce the fractions and any denominators will slide back in front of the x. Okay, so step 4. Let's see, 12 over 2 reduces to what?
6.
Okay. Let's see, Crystal, what am I going to get for this other one then? Does that reduce 3 halves? Okay, well, how come that's out again?
I'm trying to figure out stuff.
Oh. Well, I agree. Why don't you, if you need to do that, why don't you go ahead and step out in the hall? Okay, so we get x minus 3 halves. Okay, so that one doesn't reduce, and then so the last step is slide any denominator up next to the variable, right? So that 2, we're just going to slide it up front, and what's our final answer then? We get x minus 6 times 2x minus 3, and that's our final answer. Okay, that's the process. So that's what this second sheet is about. The second sheet is just specifically, the process of factoring where A is not equal 1. So we're out here at 20, right?
We're already here at 19.
19, oh, okay, well, we don't have time.